You know, have you ever stopped to think about how your phone, with its tiny battery, can possibly last all day? Or how your laptop's processor, hungry for power, doesn't just, melt? Well, the answer is this tiny, unsung hero of the electronics world, the DC to DC converter. You might also hear them called switching power supplies. Today, we're going to pull back the curtain and demystify these absolutely critical components that, honestly, make our modern world spin. So, let's jump right in. So, to really get why switching regulators are so amazing, you first have to look at let's call it the brute force method, the linear regulator. Imagine this. You've got 10 volts coming from your power source, but the chip you're powering only needs 2.5 volts. What does a linear regulator do? It basically acts like a resistor you can tune, and it just burns off that extra 7.5 volts as pure wasted heat. That's a staggering 75% of your power just gone, vanished into the air. It works, sure, but it's incredibly inefficient. The switching regulator, though, that's the smart, elegant solution. It uses a super high-speed switch to get the same result with almost no waste at all. All right, so here's the plan for our journey today. First, we're going to dig a little deeper into that whole inefficiency problem. Then, we're going to meet the absolute workhorse of the industry, the buck converter. After that, we'll see how we can go the other way, boosting voltage and even flipping it upside down. Then we'll get practical and look at what happens in the real world with design losses. We'll even touch on some of the cool math that makes this all possible, and we'll wrap it all up with a handy toolkit that summarizes the whole shebang. Okay, let's get into our first section, the inefficiency problem. This is all about really understanding the fundamental reasons why switching converters aren't just a nice-to-have, they're an absolute necessity for pretty much any modern piece of electronics you can think of. So the whole idea here revolves around using a transistor as a perfect switch. It's either all the way on or all the way off. And in theory, if a switch is perfect, it wastes zero power. But if you just switch your power on and off really fast, you don't get a nice, clean voltage. You get this choppy, pulsed waveform, and our electronics would absolutely hate that. The secret to fixing this comes down to two magic components: an inductor, which hates changes in current, and a capacitor, which hates changes in voltage. You put them together, and they act like a kind of electrical shock absorber, smoothing out all those sharp pulses into the steady, stable DC voltage our devices crave. So, how do we actually control the final voltage we get at the output? Well, we use a concept called the duty ratio, and we usually just call it D. It's actually incredibly simple. It's just the fraction of time the switch is on during one full cycle. So if your switch is on for half the time and off for half the time, your duty ratio is 0.5, or 50%. This is our main control knob. By tweaking exactly how long that on pulse is, a technique called pulse width modulation, or PWM, we can dial in the output voltage with incredible precision. Now, pay close attention, because this next idea is maybe the most important tool we have for understanding any of these converters. It's called volt-second balance. It's a fundamental law of physics for inductors. It says that for any converter that's running in a stable, steady state, the average voltage across the inductor over one complete switching cycle has to be zero. Think about it. The positive voltage it sees when the switch is on has to be perfectly canceled out by the negative voltage it sees when the switch is off. This one simple rule is the secret key that unlocks the math for every single converter we're about to look at. So let's see how these principles come together in section 2, where we're going to meet the buck converter. This is, without a doubt, the simplest, most common, and most fundamental switching regulator out there. Its whole job is to take a higher DC voltage and efficiently step it down to a lower one. And here it is, the classic buck converter. At first glance, it looks almost too simple, right? You've just got four main parts: a high-speed switch, which is usually a MOSFET, to do the chopping, an inductor to store energy, a diode, which acts like a one-way valve for current, and a capacitor to smooth everything out at the end. The real magic isn't in the parts themselves, but in how this simple arrangement works together to step down voltage so efficiently. So, how does this thing actually work? Let's break it down into two moves. First, the switch flicks on. Current flows from your power source through the inductor and out to your load. During this time, the inductor is building up a magnetic field. It's storing energy, and the current through it is ramping up in a straight line. Then the switch flicks off. The input is totally disconnected. But that inductor, its magnetic field starts to collapse, and it insists on keeping the current flowing. It has momentum, so it forces that diode to turn on, creating a new loop for the current to keep flowing to the load. During this phase, its stored energy is being released, and the current ramps down. And this cycle just repeats thousands or even millions of times every second. And you know what the most beautiful part is? When we apply that volt-second balance principle we just talked about, all of that complexity, the ramping up and ramping down, it all just melts away and simplifies down to this one beautifully elegant equation. The output voltage is simply the duty cycle, D, times the input voltage. That's it. You want half the voltage out? Just set your duty cycle to 50%. It's this direct, predictable relationship that makes the buck converter such a reliable and amazing workhorse. Now, there's one really important real-world detail we have to talk about, and that's how the inductor is behaving. Most of the time, we want the converter to operate in what's called continuous conduction mode, or CCM. That just means the current in the inductor is always flowing. It ramps up, it ramps down, but it never actually hits zero. But what happens if the device you're powering is in sleep mode and isn't drawing much current? At these really light loads, the inductor might fully discharge all its energy before the switch turns back on. This is called discontinuous conduction mode, or DCM. And when that happens, our nice simple Vout equals D times V in equation, it doesn't work anymore. The behavior changes and the output voltage can actually start to climb, which is something designers have to be really careful about. So we've mastered stepping voltage down. But what if we need to go the other way? What if we need more voltage than we started with? Well, that brings us to section 3, boosting and inverting voltage, where we go way beyond the basic step down. Say hello to the boost converter. Its job is to step voltage up. And look at this. It's the same parts, just cleverly rearranged. Check it out. When the switch is on, the inductor is connected directly across the input source, and it just charges up, storing tons of energy. But when the switch opens, that collapsing magnetic field generates a voltage across the inductor, and now that voltage is in series with the input source voltage. It's like stacking two batteries on top of each other. And together, they push current out to the load at a much higher voltage. And once again, when we apply our secret weapon, volt-second balance, we get the transfer function for the boost converter. The output voltage is the input voltage divided by 1 minus the duty ratio. Now just look at that denominator for a second. As our duty cycle D gets closer and closer to 1, that denominator, 1 minus D, gets incredibly tiny. And when you divide by a tiny number, what happens? The result gets huge. Theoretically, as D approaches 1, the output voltage could shoot towards infinity. Of course, real-world parts can't handle that, but it just goes to show you the incredible power this topology has to boost voltage. All right, now for what might be the most versatile of the basic 3 converters, the buck boost. This little guy can produce an output voltage that is either lower or higher than the input. But it comes with a crucial and sometimes confusing twist. It inverts the polarity. That's right, you put in positive 5 volts and you get out a negative voltage, like negative 12 volts. This isn't a bug, it's a feature of the topology, but it's something you absolutely have to remember when you're using one. Now, beyond these big 3, there's a whole family of other amazing converters. For instance, there's the choke converter. It's really unique because it uses a capacitor as its main energy transfer component, not the inductor, which can result in super low electrical noise. And then there's the SEPIC converter. This one is really popular because it gives you the same step-up or step-down flexibility as the buck boost, but it gives you a positive non-inverted output. This makes it absolutely perfect for things like battery-powered devices, where the battery starts at, say, 4.2 volts and then drops down to 3 volts as it discharges. If you need a stable 3.3 volts the whole time, the SEPIC can handle that transition from bucking to boosting seamlessly. So far, we've kind of been living in a perfect world with ideal components. But for Section 4, we need to get real. It's time to move from the clean world of theory into the messy, practical reality of real-world design and all the little losses that come with it. Let's start with the output capacitor. On a diagram, it's just this perfect little bucket for storing energy. But in reality, every single capacitor has a tiny bit of internal resistance. We call it equivalent series resistance, or ESR. Now, why does that matter? Well, remember that the inductor's current is constantly ramping up and down. That ripple of current has to flow in and out of the capacitor. And when current flows through resistance, you get a voltage drop. And in many, many designs, the voltage ripple caused by current flowing through this tiny ESR is actually the biggest source of noise on your output. This is why you always hear about using high-quality, low ESR capacitors. It's not just a suggestion, it's absolutely critical. Okay, let's talk about another huge source of inefficiency, that diode. A normal silicon diode, every time current flows through it, has a forward voltage drop of around 0.7 volts. That might not sound like much, but it's like a leaky faucet constantly dripping away power as heat. The modern high-efficiency solution is called synchronous rectification. The idea is simple but brilliant. We throw out that leaky diode and we replace it with another super efficient MOSFET switch. Then we just have to time it perfectly so it turns on and off exactly in sync with the main switch. And the impact this has is just massive. A modern MOSFET can have such a low on resistance that the voltage drop across it is almost zero. Just think about it for a second. If you're designing a power supply for a modern processor that needs 1.2 volts and you're losing 0.7 volts across a diode, you're wasting more than half your power as heat. That's just unacceptable. By swapping in that synchronous MOSFET, designers can easily push their efficiencies well above 90, even 95%. This isn't some minor improvement. This is the core technology that makes all of our low-voltage, high-power devices even possible. Okay, for Section 5, don't worry, we're not going to break out the calculators and do a full-blown math lecture here, but we are going to briefly touch on some of the advanced techniques engineers use to model and analyze these incredibly complex, constantly changing circuits. This is really the math behind the magic. So how on earth do you analyze a circuit that literally changes its own wiring diagram thousands of times a second? It's like trying to understand a moving car by just looking at one picture of it parked and another of it flying by at 100 miles an hour. The solution is this really clever mathematical trick called state-space averaging. Engineers write out the equations for the switch-on state, and then they write out the equations for the switch-off state. Then they mathematically blend them together, weighted by the duty cycle, D. And what you get is a single averaged model that behaves just like the real switching circuit, but it's linear and much easier to analyze. This is what lets them design the rock-solid feedback control loops that keep your output voltage perfectly stable. Another absolutely vital tool is Fourier series analysis. Remember how a buck converter draws current from its source in these sharp, sudden pulses? Well, that choppy current is incredibly noisy, electrically speaking. It can inject all sorts of garbage back onto the power line and mess with other electronics. Fourier analysis is a mathematical tool that lets us take that messy pulsed waveform and break it down into its individual ingredients, the main switching frequency and all of its higher frequency echoes, called harmonics. Once engineers know exactly what frequencies the noise is at and how strong it is, they can design the perfect input filters to clean it all up and make sure the device can pass all those strict regulations about electromagnetic noise. Whew! We have covered a ton of ground. So, for our last section, let's just take a moment to pull everything together into a nice, clean power conversion toolkit. This will be your summary of the core converter types we've talked about. All right, here it is, your DC-DC converter cheat sheet. It's pretty straightforward. The buck converter, its job is to step down and it gives you a normal positive output. The boost converter, its job is to step up, also with a positive output. The buck boost, this is the one that can go either way, step up or step down. But you have to remember its big twist. It gives you an inverted negative output. And finally, the CPIC. It can also step up or down, but it gives you that non-inverted positive output, which is why it's so perfect for those tricky battery applications. This table right here is your go-to guide for picking the right tool for the job. So the next time you pick up your phone or flip open your laptop, take a second to think about the fleet of tiny, incredibly sophisticated power plants working tirelessly inside. These principles we've talked about today, from the beautiful simplicity of a buck converter to the clever math of state-space averaging, are exactly what makes it all possible. If you enjoyed this deep dive and found it useful, do me a favor and hit that like button and subscribe for more explainers just like this. It really helps out the channel. And I want to hear from you down in the comments. Which device you own are you now most curious about? And what power electronics topics should we break down next? Maybe a deeper look at control loops or how to actually design with a CPIC converter? Let me know below. Thanks so much for watching.